Yeah.
I should not wait my
Maybe give me a sign. Well, thank you, Xavier. So first, I would like to thank the organizers for the kind invitation, in particular Guilhem, and to give me the possibility to show you some work we did several years ago. So you will see some boundary layers, and it's joint work with Marie Fage from ENS Paris. She was here last week, and with Natasha and Vienne Vanyen from Freie Universität Berlin. And I'm going to show you some results on energy dissipation caused by boundary layer instability at vanishing viscosity. So we're interested in particular in very high Reynolds number flows, and the outline is the following. So first I'm going to start with D'Alembert's paradox. I think most of you know about it, that mathematicians have shown that birds are not able to fly. But if you're looking outside, that's not true. In fact, birds can fly. Huh? So then the next part, the outline, we are going to look at dissipative properties of vortices in two-dimensional wall-bounded turbulent flows. And finally, some conclusions and open questions. So about D'Alembert's paradox. So already Euler, a long time ago, 1745, he was writing a treatise on new principles of Ganowy, highly fashionable right now, unfortunately. But he had already noted at that time that potential flows exert no drag on moving bodies. So he was writing the boat would be slowed down at the prow as much as it would be pushed at the pool. And then D'Alembert, a long time ago, again, 1749, was working for a prize at the Berlin Academy, and he wrote that it seems to me that the theory developed in all possible rigor gives, at least in several cases, a strictly vanishing resistance, a singular paradox which I leave to future geometers to elucidate. There's a nice book, if you're interested in the history of hydrodynamics, by Olivier Damigol. So history of hydrodynamics from Bernoulli to Prandtl. So you will learn a lot about history. Now, what's the problem with walls? So maybe we should also define the boundary layer. Which one is working, the green one or the black one? So if you have a wall, what you can see here, and at the wall, in fact, the velocity is equal to 0, and here you have some free stream velocity. So the velocity profile goes to 0, and when you have 99% of the free stream velocity, we call this part the thickness of the boundary layer, the delta. And that means for boundary conditions, what we have in viscous fluids, we have Dirichlet boundary conditions. From a mathematical point of view, that means we have non-penetration, so the fluid cannot penetrate into the wall, and parallel to the wall, it also vanishes, and these boundary conditions are called the so-called no-slip boundary conditions. If you have no viscosity, then in fact you can have slip boundary conditions. That means your fluid perfectly slips along the wall. And there's also another boundary condition a little bit later, developed by, proposed by Navier in 1822, the so-called Navier boundary condition. And here, in fact, you have both cases included. So if you introduce a parameter alpha, which is called the slip length, and when the slip length is equal to 0, you get no slip. And when the slip length is equal to infinity, you get perfect slip boundary conditions. And these boundary conditions are also quite attractive for numerical simulations. And in some cases, Navier boundary conditions must be used. But the toughest ones are the no-slip boundary conditions where all velocity components are vanishing. Now let's look at the Navier-Stokes equations. We've already seen several times this and last week. So we have our Navier-Stokes equations here written in the non-dimensional form with a Reynolds number, where you have the viscous term, the Laplace operator in front of you. And we're interested in the limit when Reynolds is becoming very, very large. That means when the viscosity of the fluid is tending to 0. And what we get when you're taking the limit, so you make Reynolds equal to infinity, then the second order term vanishes. It's called a singular limit because the character of the equations is changing. We have no second derivative anymore. And then you get the so-called Euler equations, where in fact you don't need the boundary conditions for the wall parallel direction. You only need the non-penetration boundary condition. And the question is, when you're looking at the solution of Navier-Stokes and you're making Reynolds larger and larger, do you get the solution of the Euler equations? So this is the general problem, what people are asking for. And in this talk, I would like to give you some ideas about it, and also for maybe not only for the young people, if you want to make some money. You know, there's a famous millennium prize problem. So the Clay prize, you can get $1 million. So if you're smart, let's work on it. It's about existence, global existence and smoothness of the Navier-Stokes equations, which is still an open problem. So mathematicians were not yet able to prove it. And we had a nice conference already some time ago in 2007, organized by Uriel Frisch. And we made a poll, in fact, voting if people believe there are singularities in Euler and Navier-Stokes, and the majority was saying, well, there is no singularity in Navier-Stokes, and for Euler it's a little bit sharper. So we had 18 against 16 votes, but that's of course not science. It's just the personal conviction that people are saying, do we have singularities or not? So maybe we should vote who thinks there are singularities, but that's not the answer. It's still open. So if you're interested in, please spend your time working on that. Then I would like to recall a little bit of fluid mechanics. I think probably you already saw that, the flow past the cylinder. So you have an inflow, you have an outflow, and you have different regimes. You have the laminar regime. So when you're having breakfast, you have a lot of honey. It's very viscous flow. So you get a very smooth flow around the cylinder. And then when viscosity is becoming smaller, so you put your honey into, you're heating your honey, let's say, then it's becoming more liquid, and then you're considering the flow, you get some transitional regime. So there are two circulating vortices which are formed behind, and then when you're increasing the Reynolds number, it's becoming weakly turbulent. You get vortex shedding. That means the vortices detach and traveling down flow. So Kalman vortex sweep, what you get, and when Reynolds number is even becoming larger, then you get a turbulent boundary layer. So you have vortices in the boundary layer, and you get a wake flow. And that's strongly turbulent and mixing. And we are interested in the limit when Reynolds tends to infinity. So very, very large Reynolds number. And the question is, well, for Euler, we know there's no drag, no force on the cylinder. And for Navier-Stokes, we always have a drag force. And just to recall, we saw that already for pipe flow here, or for channel flow. In fact, in the laminar case, you have this parabolic velocity profile, but in the turbulent case, you get a very thin boundary layer, so you get almost a constant velocity profile, and you have very localized boundary layers, which are difficult to resolve also numerically, because in many cases we want to do computations. And then there's another quantity we're interested in, the so-called energy dissipation rate, and that is taken from the paper from Srini in 1984. So where you plot the energy dissipation rate, so epsilon times the length scale divided by u cube. And then when Reynolds is increasing, energy dissipation rate decreases, but it does not go to zero. Then when Reynolds is sufficiently large, you get the constant value. And the same is true also, let's say, in numerical simulations. So people were doing homogeneous isotropic turbulence for many years, and there's always people are always hunting for higher and higher resolution, claiming larger and larger computers. I think now currently we are at 32,000 cube computations, what PK Young is doing at Georgia Tech. But already in 2003, Yuki Kaneda and his team, they did computations on the estimator using 4,000 cube computations. When you're plotting again the energy dissipation rate, you see the decay of energy dissipation rate, but then it becomes constant and go quite high Reynolds numbers. And there is some evidence, in fact, that Navier-Stokes does not converge towards Euler. because for Euler you have no energy dissipation. Energy is conserved. And then there's another famous guy around, Ludwig Prandtl. He spent a lot of time on boundary layers, and many of you probably know the Prandtl theory of boundary layers, and I would like to give you some ideas of his theory. So it's also already quite old, in 1904, and he presented that at the International Mathematical Congress in Heidelberg, close to my hometown, in fact. And he was saying, well, the viscosity is supposed to be so small that it can be disregarded wherever there are no great velocity differences. Means far away from the boundary, we don't need viscosity. So we only need the viscosity when we're close to the boundary. That means the most important aspect of the problem is the behavior of the fluid on the surface of the solid body. And there is the thin transition layer. The great velocity differences will produce noticeable effects in spite of the small viscosity constants. So close to the boundary, something happens. When this applies, the problem of the implicit limit is solved everywhere except inside the viscous boundary layer. So we can split the problem into Euler equations far away from the boundary, and in the thin layer, we're going to solve the viscous equation, and it's called the Prandtl's boundary layer equation. And he also made a prediction and gave arguments for the thickness of the boundary layer and scales like 1 over square root of Reynolds. Well, now let's look at the limit of validity of Prandtl's theory. Well, it works well. In fact, when we have attached boundary layers, and maybe here what you can see is airfoil with different angles of attack, and experimental data, and you can see, well, here you have nice big lines, your boundary layer is attached. If you look at higher angles of attack, the boundary layer will detach and vortices are formed. And Prandtl's theory only holds on the left-hand side and not on the right-hand side. Maybe I should go back again. Is that working? No. Oh, yes. Now you can see it. And then there's another mathematical theory which is not so well known by Kato, Japanese colleague, so in 1984, and he gave some rigorous results for Navier-Stokes convergence towards Euler equations. That's quite interesting. So he's claiming that, proving that the Navier-Stokes solution converges towards the Euler solution if and only if the energy dissipation vanishes. And if and only if this happens in the boundary layer of thickness, which is now proportional to 1 over Reynolds. So it's much smaller, much thinner boundary layer compared to Prandtl's boundary layer. So it's 1 over Reynolds, not 1 over square root of Reynolds. And the energy dissipation, in fact, vanishes uniformly in time, what you can see here in the limit when Reynolds is going to infinity. And the result, in fact, if Kato's theorem applies in this context, this requires, in fact, that we need much finer grid resolution close to the boundary layer, and that will make the computations much more expensive. And we are going to check this approach in the following in more detail. So now, in the second part, we're going to look at dissipative properties of vortices in wall-bounded two-dimensional turbulent flows. We would like to show you some illustration here. It's a computation, what we did. Some more can speak now, but you can see vortices. In fact, red vortices go clockwise, counterclockwise rotating, blue vortices clockwise rotating, and you see the formation of a very thin boundary layer here. So this is the wall, which we can see here. We have a very thin boundary layer which becomes turbulent. We see the detachment, formation of vortices at the boundary, and then the attachment of the vortices into the bulk flow. That is the motivation. Sorry for the qualities.
It's better on the screen.
Really? It's different? Yeah? Okay. It's yeah? Okay. But sometimes, I don't know, there's something with the codec. And there are also experimental studies, for example, the dipole crashing on a wall. We're going to visit in the following. So you can generate a vortex dipole which crashes the wall. So the vorticity is generated and then bounces back the bulk flow And you see the highly complex nonlinear dynamics and the formation also of opposite sign vorticity, opposite sign vortices. So you can nicely identify in fact what happens in the dynamics here, also in experimental studies, while eventually flow becomes three-dimensional. And we are going to analyze this case in more detail. So what we did here for different Reynolds numbers, we're studying, in fact, the vortex dipole, which is illustrated here. Time goes by, if we go from left to right. But maybe let's look at the movie. Yeah. Oh, it's working. See the dipole, which is forming. Vorticity stripped off, running to the left. The dipole hits the wall, which is here. Right, so now it's coming. So still Euler is good, and now Euler is not good anymore because you can see the formation of very thin boundary layer, see the formation of very intense vortices. We just look at the values here. So it goes between minus 300 and plus 300 for vorticity at the beginning. But when the dipole hits the vorticity values are becoming very, very large. You can see here we are already 2,000 and more very high values. So we are going to study this now in more detail. So the question is, in fact, about the intensity of the vortices. Are these distributive structures? And what we are going to see in the following. You see directly the nonlinear dynamics, formation of very intense vorticity here. Then you can see the detachment of the boundary layer. And that can be analyzed. So we are looking now at the energy evolution for different Reynolds numbers. So when we have Reynolds of 1000, we have a blue curve. The dissipation of energy goes down, and the Reynolds number is increasing. You get less and less dissipation. And when you go then to the Euler case, let's say you get no dissipation, only see dissipation, and the dipole hits the wall, so you get a very strong dissipation of energy when you have this interaction. And what I would like to show you in the following is in the energy dissipation here for the different times and for different Reynolds numbers. So here you have the different energy. The horizontal axis, we have with different Reynolds numbers. So low Reynolds number on the left, high Reynolds number on the right. And you can look at the dissipation of energy at early times. So when not much happens, you have no interaction. In fact, with the boundary with the wall, you see the decay of energy. But we can see when at later times, so once you have the hit of the dipole in the wall, you can see energy dissipation is slowing down. It seems that energy dissipation becomes the constant, so it's not depending to zero. So this is a first indication what we have for increasing Reynolds numbers. And like our experiments I just showed you for the dipole suggest that the flow remains dissipative in the invisible limit. So when Reynolds is becoming larger and larger, dissipation is not tending to zero. And the quantity to analyze that is the kinetic energy density, which can be defined locally. So you have the velocity here, and you just pointwise define the energy density. It also fulfills the transport equation, be written down. So you just take Navier-Stokes, you multiply by u, then you can get the equation for the kinetic energy density, and you have like two terms related here. This term, which is related to the gradient of the velocity. And this two terms here are called the local dissipation rate in the Navier-Stokes equations. And if we are looking now at the energy dissipation rate in the different regimes, so first with the attached vorticity layer, so at early times, that again is a function of the Reynolds number, we can see that the energy dissipation rate tends to zero, while we have in the other case, when we have the detachment of our vortices from the boundary layer, we can see if we increase the Reynolds number, the energy dissipation that does not tend to zero. And looking at the scaling now, so the energy dissipation again as a function of the Reynolds number,
we can see that at early times we have the Prandtl scaling, so 1/square root of Reynolds scaling, and at later times we find in our numerical simulations the Kato scaling, that means scaling like 1 over Reynolds.
And just to look at the local dissipation rate, which is plotted here, so the wall is here, you can see you get very, very strong dissipative structures. That means most of the dissipation takes place at the vortices, which are formed at the wall and which are traveling in the flow. And that is quite interesting, because that means that the dissipation does not take place at the boundary layer, but in the vortices which are traveling inside the bound flow. That was a new result. And now in the last part of the talk, what I would like to show you are some details about the coupling between Euler and Prandtl equations. So for Prandtl model, there is typical ansatz. We are using it here on vorticity formulation. I think it's really difficult to read. It's better to read it on this side. Sorry for that. So you can develop making the asymptotic development of velocity. Here we do it for vorticity into the part which corresponds to the Euler solution, and then scale with the viscosity. So 1/square root of viscosity. We have different terms, these scale terms for the Prandtl solution. So it's an asymptotic development of the vorticity in the limit when Reynolds is becoming very, very large. And what we have then in the Prandtl-Euler model, we are solving two different equations. So we are solving two-dimensional Euler equations, so vorticity for the Euler equations, which are given here. So that is the Euler part. And we have boundary conditions, so we have velocity does not penetrate into solid wall. That means the stream function at the wall is equal to 0. And we need initial condition also for the Euler solution. So that is part 1 for the Euler equations. And the Euler equations are then coupled. First they are solved. Sorry, you can solve the Euler equations. We're using here mirror symmetry around this axis. So we have a quadrupole. And then you can, in fact, solve the Euler equations using symmetry arguments. And I think it's a movie. So we're just interested here, this part. So this is the dipole, which is crashing on the no-slip wall. And then you have perfect slip along the wall. And there's no formation of the boundary layer, because you're satisfying just the non-penetration boundary conditions. You have no generation of vorticity at the boundary. We should have played again. It was not the whole. So nice. This is artifact not from the numerics, but from visualization. So here you see perfect slip along the boundary. And then the second equations, what we have are the Prandtl equations. So you can simplify the Euler equations using this rescaling, and look similar to the Euler equations what you can see here. But the major difference what you have the viscous term, but you have the viscous term only in the y direction. So in the direction perpendicular to the wall. Parallel to the wall, the Prandtl equations do not have a second derivative. And that is a major problem, in fact, we will see later, because there's no regularization of the Prandtl equations in the wall parallel direction. So only the wall normal direction have the second derivative. But then we have the boundary conditions which are given. These are non-local boundary conditions for vorticity formulation. And also we have the coupling term. So the derivative of the vorticity of the Prandtl solution at the wall is equal to the pressure gradient in the horizontal direction, which comes from the Euler solution. So Prandtl and Euler equations are coupled. And what is used in the model typically is then that we are doing numerical simulations for Euler equations coupled with Prandtl's equations close to the boundary. And this model solution can then be compared with a full Navier-Stokes solution. This is what we're going to do in the following. Here's some details about the spatial discretization, but that's maybe not necessarily here to discuss that. We have also some additional boundary conditions. Some boundary conditions, what I was explaining you at the wall coupling term, and then we need some additional boundary conditions to close. In fact, our equations, but it's again technical detail. The Navier-Stokes solver we're using is based on Théorie in the homogeneous direction, boundary conditions in X direction, and in Y direction, where we have the wall, we're using compact finite differences and non-uniform grids here, and we're using, in fact, for the boundary conditions, two linear integral constraints, because when you are working with a vorticity formulation, the no-slip boundary conditions become non-local, and we have two enforce integral constraints to get the correct boundary conditions. This is the computational grid we're using. Well, the dipole hit attachment of the boundary layer takes place at 54 times 54, so we're using the grid which is not as fine up to t equals 54, and when we have attachment of the boundary layer, we use very fine grid to resolve the Kato layer, which is a very thin layer, 1 over Reynolds, so we need much finer discretization of the Kato layer compared to the Kanto layer. And the numerical simulation, I would like to show you. On the left, we have the Euler model. Vorticity is shown. So we have perfect slip along the boundary. What you can see here, the dipole is coming, and it slips perfectly along the boundary. There's no generation boundary layer. On the right-hand side, we have the full Navier-Stokes solution. At the beginning, both look very much the same. But then you can see in the Navier-Stokes solution, you get generation of vorticity and detachment on stroke. You get detachment of the boundary layer. And what is shown below is, in fact, the zoom of the vorticity field in the boundary layer. And you can see, again, at the beginning, you have very good agreement between Prandtl and Navier-Stokes, as long as you have no detachment of the boundary layer. And then what happens here on the left-hand side, the Prandtl equation blows up. You get a singularity in the Prandtl equation, so you cannot solve it anymore. You get not a number on your computer. You can mathematically show also that there's blow up. So next slide. And Navier-Stokes still continues because here we can patch the detachment of the boundary layer, what we have. And now, well, what I mentioned, Prandtl's equation has well-known finite time singularity around von Dommelen, Zitar, and Chen. They published that some time ago already, because the vorticity gradient and also the velocity blow up. And you can see that in numerical simulations. Here, when time goes by, you get very strong growth of the L infinity norm of the vorticity. And now, according to the theorem I mentioned by Kato, but omega 1 remains bounded up to the detachment time. And so up to the detachment time, we have a convergence effect of the viscous solution, U with viscosity, the limit when viscosity goes to 0, to the Euler solution. And what we are plotting here, again, for different Reynolds number, the maximum of vorticity over time. So for Prandtl, you can see the maximum vorticity very small, then we have very strong growth, and then you get the blow up of vorticity. And for increasing Reynolds number, you're getting closer and closer, but you still have finite value. So what does not blow up. We have no singularity in the Navier-Stokes solution. Yeah, I'm almost done. Thanks. And now for the vorticity maximum. So considering that early times before detachment and after detachment, so it's blue, we get a nice scaling proportional square root of Reynolds.
at early time. So bundle scaling is working, but once we have attachment of vorticity, we get the scaling of the maximum vorticity, like the Reynolds number. So we have a very strong growth effect of the vorticity after the detachment. And well, we can compare it now, plotting isolines here of vorticity, which are shown for Euler bundle in pink and black for Navier-Stokes. That is cut. You can see it better here of the vorticity. And you can see at early times you have good agreement, and then, well, you see some slight differences between Euler and bundle, but still you have some agreement, and the differences are reflected in the cuts because you get some oscillations in the vorticity along the boundary. So very fine scales are forming in the vorticity field along the boundary. Well, these are related to Tolman-Schlichting waves. And these high oscillations, in fact, are responsible that the bundle solution blows up because these fine scales are not damped, because in the bundle solution we have not second order term, so no viscous term in the wall parallel direction. And the last connection I would like to show here is about turbulent boundary layers. Well, there is theory by von Karman, Karman constant 0.4, which predicts the fact of the velocity profile along the boundary log profile, which is given here. So the logarithmic, the log law of the boundary layer with the friction velocity u tau. And what is interesting to point out in this context is the fact that it's related, that might be related to the Kato layer, because in fact, the behavior of the friction velocity implies that the boundary layer thickness, according to the logarithmic wall law, scales like 1 over Reynolds and not like 1 over square root of Reynolds. So there is already in von Karman's wall law some indication that we need finer scales to be resolved close to the wall. And with that, I would like to conclude. So what I tried to show you in this talk is the production of distributive structures, which are a key feature in boundary layers, especially when you have the detachment, and we're interested in the vanishing viscosity limit. What we've also seen is that the bundle solution, the viscous bundle solution, becomes singular when the boundary layer detaches. And what we've also seen, so we can use the implicit Euler solution as long as we have no detachment of the boundary layer. So the Euler model is okay in the limit, but once we have detachment of the boundary layer, then we have no convergence anymore. And the interesting feature I try to show you is that the detachment process involves, in fact, spatial scales in different directions. So you need fine scales in the wall normal direction, but also fine scales in the wall parallel direction. And these are much finer than the classical estimation by bundles. We need 1 over Reynolds for the thickness of the boundary layer and not just 1 over square root of Reynolds. And now for still conclusion. So the detachment dynamics are very different from the dynamics of finite time singularity developing Hunt's equation. So we have non-locality in the wall parallel direction. We have the formation of small scales like 1 over Reynolds in different directions, so with X and in Y direction, and the pressure plays an essential role. And if you're interested in the 2 publications where we detail that, it's already some time ago. And the open question, and that's my last slide, is that the numerical results, in fact, suggest that the new asymptotic description of the flow beyond the breakdown of the bundle regime is possible. So studying it might help to answer some of the questions which are still open. So would Navier-Stokes solution lose smoothness after the detachment of possible singularities? The limit when the viscosity goes to 0, of course, and would it converge to a weak singular distributive solution of Euler's equation? And you
Remember, maybe for Berger's equation, what we're typically studying, we have shocks which are dissipative, and we are selecting a solution which is dissipative by imposing the so-called entropy condition. Nothing to do with entropy, but you have to select the dissipative solution. And that might be, in fact, a new resolution of D'Alembert's paradox in terms of the production of weak similar dissipative structures due to the interaction of fully developed turbulent flows with walls. And with that, I would like to thank you for your attention, and I'm open for questions.